Okay, we're back with video 8, section 2.3 from Math 196, spring 2014, parabolas and completing the square. So first we'll start with a few words about parabolas. We have two ways to write the formula for a parabola. This is sort of the standard quadratic equation kind of formula, ax squared plus bx plus c equals y. We can turn this formula into something called the vertex form. So that's y equals a x plus h quantity squared plus k. The nice thing about vertex form is that you can read off directly from the formula how the graph of y equals x squared has been moved, right? So the h is inside the parentheses. That means it's been moved left or right, depending on whether h is positive for moving left, negative for moving right. The a tells you how much it's been scaled by and whether or not it's been flipped over the x-axis, right? If a is negative, it's been flipped, the parabola opens down. If a is positive, it's still upright. And then the k tells you if it moved up, that would be a positive k, or moved down, a minus k. And so something called completing the square will take a quadratic kind of equation and turn it into a vertex form. So just a note before we get started, problems 9 and 10 in this section are very much like problems from the previous section. They give you a formula and they want you to identify the graph. Okay, so here's a parabola. What do we want to know about parabolas? What are the various properties of parabolas that we're interested in? Vertex, for this the maximum. Range, what's the formula? X-intercepts, y-intercepts. Those are the things that we want to know about a parabola. Where is the vertex? The vertex is, in this case, the very top of the graph. If you have a parabola that opens down, it would be the very bottom of the graph. So vertex, it's a point, so it's got an x-coordinate and a y-coordinate. X-coordinate 3, y-coordinate is 1. Maximum, when we refer to a maximum, we're referring to the y value. So the maximum is y, and that occurs at x equals 3. What's the range? Well, the range is everything less than or equal to the maximum. So y less than or equal to 1, or if you like interval notation, you can write it like that. So the highest point on the graph is at y equals 1, and so the range is all the y's less than that. What's the formula? Well, we know that it's been moved right 3 and up 1, right? Because the parabola would start here. And if the vertex has been moved over to here, that's right 3 and up 1, it's been flipped, and has it been rescaled? So we know how much has been moved. Right 3, up 1, flipped. How do we tell if it's been rescaled? Well, here's where our vertex is. If we go 1 unit to the right, and be careful about these pictures sometimes, each black line is 1 unit right. So 1 unit right, and how far down do we go? We start at 1 and we go down 2. Horizontal lines, each gray one is 1 unit. So we go right 1, down 2, so it's been rescaled by a factor of 2. And now that's all the information we need to be able to write down the formula for this thing. If we can get that to scroll down a little bit. So y equals minus 2, that's the scaling, and the flipped is the minus sign. Been moved right 3, so that's a x minus 3 inside the parentheses, and a plus 1. So there is our formula. What is the y-intercept? How do you find a y-intercept? Set x equal to 0 and solve for y. Finding the y-intercept is always easier than finding the x-intercept. So the y-intercept is minus 2 times 0 minus 3 squared plus 1. This is minus 3 squared is 9, so we get a minus 18 plus 1, minus 17. And if we look here, minus 17 is where it crosses the y-axis. So that's our y-intercept. X-intercept, how do you find that? Well, if you remember what we learned about lines, you find the x-intercept by setting y equal to 0 and solve for x. And so if we set y equal to 0, we get 0 equals minus 2 x minus 3 squared plus 1 . And you do the square root method on that to solve it. And since we're losing losing a little bit of space here, we'll come up here, move the negative thing over to the other side. So we'll take this term and move it over to the other side, divide both sides by 2, take the square root, don't forget your plus or minus, 1 over square root of 2, so x equals, if we add a 3 to both sides, that would be x minus 3 there, 3 plus or minus 1 over square root of 2. And so 1 is here, 1 is here. Note that the vertex is always halfway between the two roots. Right? So 3 plus 1 over square root of 2 gives you one root, 3 minus square root of 2 gives you the other root. Or the x-intercepts. X-intercepts are often called roots. And so this is what we can do. Given a graph, you can find the vertex, the range, spelled with an E, not with a Y, maximum, how it's been moved. Once you've figured out how it's been moved, written up, or flipped, or scaled, you can write down the formula. Once you have the formula, you can find the y-intercept and the x-intercept. The nice thing about vertex form is that you can use the square root method to find the x-intercepts instead of having to use the quadratic equation. So, here's the question. If I've got a quadratic equation, how can I find the vertex form? Once I have the vertex form, it's easy to graph, and then I can find the vertex, the range, and the x and y intercepts easily. But I need to convert this to vertex form. So, completing this square, what's the procedure going on here? We take our equation, y equals x squared plus 4x plus 2, and the key number here, and we'll do a little calculation here in red, is this 4. So we take the coefficient of the x, that's a 4, and we cut it in half. That gives me 2, and then I square that, which gives me 4 back again. So I'm going to insert 0 into my equation, but I'm going to do it in a really sneaky way, like that. So what have I done? Have I actually changed anything? No. If I add 0 to one side of an equation, that doesn't change the equation, right? And 4 minus 4 is 0. But I'm doing this in sort of a sneaky way. Why do I want to do this? Because now this, the first 3 terms, can be factored in a very nice way. And then minus 4 plus 2 is minus 2. Right? And that's the trick to completing the square. You take the coefficient of the x, cut it in half and square it, then add and subtract it directly after the 4x. And then the first 3 terms become a perfect square, and then you can just add the other 2, and you get this. And this is nice. We know now that our function has been moved left. Plus 2 is left 2 units. Down 2 units. So this plus 2 means left 2 units. This minus 2 means down 2 units. Not flipped or stretched. How do we know it's not flipped? The coefficient here is positive, so it's not flipped. And it's not been rescaled at all because there's no coefficient out front, right? And so this is a equals 1. This is dealing with non-scaled parabolas. Great. And now we can do all the things we want to do. Graph the function, vertex, range, x and y intercepts. So if we graph this function, what is it going to look like? Here's my x-axis, here's my y-axis. We go, oops, let's move my y-axis over a little bit. Left 2 units, 1, 2. Let's move left, move down 2 units, 1, 2. So my graph will go, remember there's 3 points you want to remember about a parabola. The vertex will be there, that'll be the bottom of the graph. We go 1 unit right, we go 1 unit up, and we'll put in a 3 there. And let's see, I'm doing blue. And if we go, no, that should be blue, not black, but whatever. So for a parabola, what we've done is we've taken the parabola that had started out here. We moved it 2 units over, 2 units down, so that's where the vertex is. Since it's not rescaled, 1 unit to the right means 1 unit up. And so what does my graph look like? There's my graph. So this is either x, well, this is my x-axis and the y-axis. We now have 2 formulas for this function. You can either call it this, or right, if you FOIL this out, you get this. And so completing the square is sort of unfoiling in a very specific way. Great. So what's my vertex? Well, 2 left, 2 down, minus 2, 2, and again you can read that off from here. 2 units left, 2 units down, minus 2, minus 2. That's my vertex. What's the range? It opens up, so it's y is greater than everything, than the bottom of the graph. And the bottom of the graph is at y equals minus 2, so my range is bigger than that. So y is greater than or equal to minus 2. What else did I want to know? X-intercepts and y-intercepts, I believe. Come on, back up. There we go. Vertex, range, x and y-intercepts. So, y-intercept, set x equals 0, solve for y. Got 2 formulas though. Which is the easier one to do? Well, this formula is. If I just set x equal to 0 into this equation, what do I get for the y-intercept? Well, 0 plus 0 plus 2. So there's my y-intercept is 2. X-intercept, set y equal to 0, solve for x. And this is a better formula to solve for the x-intercepts because we can just use the square root method to find the root of that. So to find the x-intercepts, set y equal to 0. 0 equals x plus 2 squared minus 2. And that's pretty easy to solve. 2 equals x plus 2 squared, plus or minus square root of 2 equals x plus 2. And so finally x equals minus 2 plus or minus square root of 2. Right? And so where are the x-intercepts? Minus 2 plus square root of 2 means we go 2 units to the right, and that's here. Minus 2 minus square root of 2 means we go 2 units to the left, that's there. Again, the vertex is halfway between the roots. Okay, so completing the square, this is when you have an unscaled a equals 1 quadratic, so coefficient of x squared is 1. Take half of the coefficient and then square that, add and subtract. Okay, what about if a is not equal to 1? So problems 23 through 26 in section 2.3. So here a is minus 5. So how do we deal with this? Well, we're starting with y equals minus 5x squared plus 30x minus 39. We want to graph this, rewrite it in vertex form. So we can graph it, find our vertex, range, x and y intercepts. Okay, So since a is not equal to 1, it's minus 5. What we'll do first is divide both sides by a, which in this case is minus 5. So what do I get? I get y over minus 5 equals, well, minus 5x squared divided by minus 5, that's x squared, and so point is to get a 1 for the coefficient of x squared. 30 divided by minus 5, minus 6x. 39 divided by minus 5 is something messy, but I'm not going to worry about it. It'll be just 39 over 5. Note that all the signs change because we're dividing by a negative number. So this becomes positive, this becomes negative, that becomes positive. Great. Now we have on the right-hand side a quadratic formula, quadratic equation, or quadratic expression, I guess is technically what it is. And with the coefficient on the x squared, that's 1. And we can just complete the square like we did above. What that means is take the coefficient of x, cut it in half, and then square that. And so what does that make our equation? We still have the y over minus 5 on the left hand side, and be careful about this. What I've noticed sometimes walking around talking to people is that there's a tendency to just work on one side of the equation and just ignore the other side. When you solve an equation, always make sure you write down both sides of the equation. So what do we have? X squared minus 6x. What do we do with this 9 that we just calculated? We add it and subtract it. Plus 9 minus 9, and then we have this constant term over here, plus 39 over 5. That term is going to take care of itself pretty quickly. Great. So, completing the square, it's a little magic done. X squared minus 6x plus 9, that is a perfect square. You can factor that into x minus 3 quantity squared. Note that this number, which is actually, I forgot the minus sign, that's a equals minus 3, right? And minus 3 squared. This number here shows up inside your parabola, right? So if minus 6 is the coefficient, then it'll be x minus 3 quantity squared. Great. Minus 9 plus 39 over 5. And now we handle the 5 by multiplying both sides again by minus 5. So we get y equals, just multiply both sides by minus 5. That'll cancel out this minus 5. Minus 5 x minus 3 squared. Minus 5 times 9 is plus 45. Minus 5 times 39 over 5, where the 5's cancel and we pick up a minus sign. And so we end up with y equals minus 5 x minus 3 squared plus 6. Awesome. There's our vertex form. What does our vertex form tell us? Well, the minus 5 says it's flipped and stretched by 5, right? The minus sign tells us it's flipped. 5 tells us it's stretched by 5. The minus 5 here tells me that it's been moved right 5 units. And the plus 6 up 6 units. Okay. So what does my graph look like then? I'm not going to be particularly tidy about things. We'll just sort of say, here's 5, I need 1 unit right, 1 unit left, and then up 6. We'll say up 6 is up here somewhere. So the vertex has been moved right 5, up 6. We've been flipped and stretched by 5. So where are the 2 points? If we go 1 unit left, we should go down 5 units. If we go 1 unit right, we should go down 5 units, right? Because it's been stretched by 5. Great. So now we have the graph we can draw. It should look like that. So what's my vertex? 5, 6. What's my range? It's y less than or equal to 6, because that's the top of the graph, and we're only looking at the y's beneath that. Y-intercept, well, again, we have two equations now for the function. One is this one up here, sort of in a quadratic form, and one is this one, which is the vertex form. If I want to know what the y-intercept is, this is the easiest one to find. Set x equal to 0. 0 plus 0 minus 39, that equals y. That's way down here somewhere, so I'm not going to put that in there. What's the x-intercepts? Well, for my picture, there should be one should be just a little less than 4, and one should be a little bit more than 6. Set y equals 0, solve for x. Use the vertex form when you're finding x-intercepts because you can just use the square root method. So set y equal to 0 minus 5 x minus 5 squared plus 6. Take the negative thing, move it over to the left side. Divide both sides by 5. This is a 5. So x minus 5 squared equals 6/5. Take the square root. Don't forget your plus or minus. 6 over 5, and then add the 5 to both sides. X equals 5 plus or minus square root of 6 over 5. And that's what our two square roots are. And I didn't actually calculate what those numbers are. Okay, so completing the square. Again, if we go back one problem, we have the basic completing the square example. If the coefficient of a is 1, then you just take half of the coefficient of x, square it, and add and subtract that, and then the first three terms will turn into a perfect square. Note that when you take the half, right, plus 2, that's going to be the number that shows up inside of the perfect square, and then you have to do something to figure out what the constant term is. And once you have it in vertex form, you can read off if it's been moved left or right, up or down, whether it's been flipped or stretched. If you have a coefficient of a that is not 1, so like with this problem, divide through by the coefficient of a first. And then you have something just like the previous problem, so take half of the coefficient of x, that's the minus 3, and square it, add and subtract that, and again, just like in the previous problem, that half is going to show up inside this minus 3 shows up inside that part of the coefficient. So half of this coefficient is how much it's been moved left or right, and then you have to figure out the up or down. Is a little bit tricky. And once you have the vertex formula, you can figure out the vertex and the range pretty quickly. The y-intercept, set x equal to 0 and solve for y. The x-intercept, set y equals 0, solve for x. If you have vertex form, that's much easier to do because you can just use the square root formula to find the x-intercept. Okay, so that's the end really of the stuff for 2.3, but there's two things that I want to do. Right? One is, and so this is a bonus video, but it's just, you know, a little comment. Why is it called completing the square? So let's pretend we are ancient Babylonians. Completing the square is a really, really old technique. It was discovered or figured out, you know, by the Sumerians, so like 3000 BC or something. So suppose you want to solve this problem, x squared plus 8x equals 24. Well, factor the first one, x times x plus 8 equals 24. And the Babylonians or Sumerians or whoever figured this out looked at this and said, well, this times that, that's an area, right? It's an area of a rectangle, right? Base times height. So let us draw a rectangle. I guess we'll use the x as the base, the x plus 8 as the height. No, the x is the height and the x plus 8 is the base. And then we can, if we wanted, let's not put it quite there. We'll put it over here. Even though it doesn't quite look like a rectangle, a square, we'll say this is x and this is 8, right? If this whole thing is x plus 8, I should be able to break it up so that I get an x there and an 8 there. Right? And so the area of this part should be x squared, the area of this part is 8x. Right? 8 times x. Now this is the interesting part, because what I want to be able to do with that is say, well, So that would be step 1, and now we go over to step 2. Here's my break that I'd introduced. X, 8. I can cut that in half. Right? So let's cut that sucker in half right there. So that's a 4 and that's a 4. And remember, that was the essential part in completing the square, was to take the coefficient of x and cut it in half. So I can cut that in half. This area here is 4x. This area here is 4x, because again the height is x. Great. So what can I do with that? Well, I can redraw it. So I have x and x, that's this space. I'll leave one of the 4x's here. This is height 4. This is still x, so this area is 4x. And this area is x squared. And then we'll draw on the other one. What we'll do is we'll take this one and we'll move it underneath, right? This side is length x, so I can glue it onto this side. Great, so this is 4, this is x, and that's 4x. So I've been working so far just with the left side of the equation, dealing with the x squared plus 8, and I can rewrite this thing, this rectangle, like this rectangle. This has an area of x squared plus 4x, so that's x squared plus 8x. And this is supposed to be equal to some area equal to 24. Right, because that was the original equation. Solve x squared plus 8x equals 24. So now I'm at this point. How can I complete the square? Well, what do we got? We've got x squared. We've got, oops, that's not x squared. This is x, this is 4, this is x, this is 4. And now if I complete this square here, pens, blue pen, right there, right? Now I have a square. The side length here is x plus 4. The side length here is x plus 4. But I added a little square of side length 4, so it's an area 16. So if I'm adding a 16 to the left side, what is this equal to? It's equal to something of area equals 24 plus area equals 16. So I've took this thing and I've added a little square there to complete the square, and now I have a 16 area that I have to add there to complete the square, and I add it there. And so what does my equation now become once I have these equations? Well, this is x plus 4 quantity squared. That's this whole thing, because the side length is x plus 4, x plus 4. And what does that equal? 24 plus 16 equals 40. Sumerians didn't believe in plus or minuses. They didn't believe in negative numbers, so they didn't use a plus minus, but we'll throw that in there. Great, and so that's why it's completing the square. Right? If you think of the x squared plus 8x as a rectangle, the long side is going to be x plus 8. I can take that, cut it in half, re-glue part of that down to the bottom, and I get a figure that's just missing a square down in this part. That's the square of area 16. So if I fill that in and add it to the other side, what do I get? Well, I've got a nice square with side length x plus 4. So the area of this whole thing is x plus 4 quantity squared. And I've got an area of 40 on the other side, and then I can solve it. And that's why it's called completing the square, right? You have to complete the square by throwing in this piece. How big is this piece? It's the square of half of the original coefficient, because you split the original coefficient in half. So that's why it's called completing the square. That's why the method works. That's where it came from. It's very old. Oh, look, we have bonus video 2, Deriving with Quadratic Formula. So this also comes from completing the square. So we want to solve the equation ax squared plus bx plus c equal to 0. Solve for x. Well, let's complete the square. What do we need to do to complete the square when the coefficient of x squared is not 0? Well, divide through by a to get a coefficient. When the coefficient of x squared is not 1, we divide through by a to get a coefficient of 1 on that side. Notice that when I divide 0 by a, I still get 0. Great, so I need half of this. Half of b over a equals b over 2a. b over 2a quantity squared equals b squared over 4a. Okay. So x squared plus bx, and we add a b squared over 4a, and then we subtract a b squared over 4a, and we have a plus c over a equals 0, just completing the square. These three terms are a perfect square, and what is it? It's going to be x plus b over 2a. So x plus b over 2a squared equals, well, let's move all this stuff over, these two terms over to the right side. So we get b squared over 4a plus c over a. Oh, squared. I forgot the squared there. And if I get a common denominator, multiply top and bottom of the c over a by 4a, and that will give me a common denominator of 4a squared. So that's going to be b squared, and the c over a comes over as a minus sign, minus 4ac all over 4a squared. So hopefully you recognize the b squared minus 4ac. And now we take the square root of both sides. What do we get? Plus or minus the square root of b squared minus 4ac, not s, but c, all over 4a squared. If I take the square root of the top and the square root of the bottom, I get plus or minus b squared minus 4ac. I'll put that up on the top. Plus or minus b squared minus 4ac. Square root of 4 is 2. Square root of a squared is a. So plus or minus b squared minus 4ac all over 2a. And then finally we move this over to the right side. Minus b over 2a plus or minus b squared minus 4ac square root divided by 2a. Common denominator, we already have one, so let's just put it all over the 2a minus b plus or minus b squared minus 4ac all over 2a. Awesome. And so there is our quadratic formula. One thing to note in doing this, right, when we rewrite this in vertex form, what we get is b over 2a, x plus b over 2a squared. So b over 2a, this is how much it's been moved left to right. It's the x coordinate of the vertex. So if we go back and look at our, oops, if we can, examples, here we go. Oops. Right. B is 30, 2a is minus 5, so the vertex should be at minus 3. And in fact it was. So we'll just note this here. B over 2a equals minus 3. That's the x-coordinate of the vertex. If we go up to the previous problem, what's b over 2a? Here, b over 2a is 4 divided by 2. So our vertex is at 2. I don't know if we have another example here. Oh, this is one where we actually started with the graph. So, completing the square means taking a formula, ax squared plus bx plus c and turning it into vertex form. From the vertex form, you can figure out everything you want to know about a parabola.